Okay. All right. So last time I went on a big rant about problems and how the bit string thing was a simple problem, but we just used it for the sake of trying to wrap our head around what is a GA and how is it going to work and what's it going to do. So let's make sure we're using some like terminology and make sure we're all on the same page with some basic ideas to make sure we can wrap our head around everything as we go. We have some system. I'm using the word system very abstractly, very generally. Something, all right, which may or may not have inputs, may or may not have outputs, and something's going on. And if I want to like model this system, like if I want to try to understand it, I want to make a model of this system. And for those of you that like whoever built like a little model airplane as a kid, it's the same idea, except the model airplane is relatively simple. But instead of making a model of an airplane, I want to make a model of some system, right? A complex system, let's say. So, I mean, you as programmers at this stage, like this is a black box system. It's got some input, it produces some output. What the hell is going on the inside? I don't know. But this system receives some number of inputs and produces some form of operations based on the inputs and may or may not be producing some output. And like you're familiar with this in terms of writing functions, right? Like you can think of this model as a function. We've got some function, it has some parameters, our inputs, and it returns some value, that's the outputs. And we like to think about systems in this abstract way. Like you might be looking at this and saying, like, yeah, no duh. But at the end of the day, it's nice to kind of think of these things at a certain level of abstraction where you get like a nice level of granularity where you can think of the individual parts without getting lost in too much detail or too little detail. So this is a nice level of abstraction to talk about any general system. So yeah, it helps us distinguish the parts, the input, the model, and the output. For a concrete example, consider a simple problem like calculating a grocery bill. The input are like the items and their prices that we want to buy. The model is some function to calculate the price plus the sales tax, and the output is the total sales bill. Or designing an aircraft wing, for example. I want to model that. Well, maybe if I'm trying to like model and understand an aircraft wing, I'm going to have some input, which might be like the shape of the wing. The model is going to be the equations of complex fluid dynamics. And the output is going to be like estimates of drag and lift. I'm no expert on this stuff, but I'm just using this as an example. Or photosynthesis. Okay, so, plants make their own food. Input is light, carbon dioxide, and water. The model is light reactions in the Kelvin cycle, which it doesn't matter. It's magic that plants do. And the output is oxygen and sugar that the plants eat, and we eat. And calculating time it takes to drive to work. Input is the route taken, model is, well, our universe, and output is, well, the total time it takes, right? This is kind of a funny one to think about because like the model, there's no real, like my model of how long it would take to work is relatively simple just because we're so familiar with our environment, but the model would be our environment. So as computer scientists, we often like to think of these things as functions, like I was just saying, and when you take some real world thing, in vivo, which scientists love to use Latin, in vivo just means like in real life type thing, and we try to model it in the computer, in silico. Again, this is actual Latin, this is bullshit Latin, but the scientists like to feel smart, so they say in silico. So with a known model, the output can be calculated with any valid admissible input. It's simple. You have a function. I have valid input, the model can calculate the output. Always, 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 always. You try to break it, well, maybe the only way you're going to break it is if you give it invalid inputs or something. Pretty straightforward, right? This shouldn't be shocking to you. All I want to do is make sure we're all on the same page before we continue. Any questions about any of this? Observations, thoughts, or anything? All right. So let's say we're doing optimization. And I want to be clear, what I'm about to say, I'm talking in general. We could probably find a bunch of exceptions to these things, especially because the boundaries between these classifications can get a little fuzzy, but I'm speaking in relative generality. So if we want to optimize something, right, given a system, let's say I want to, okay, so optimization takes place when we have the model and our output objective is known, but the input is not. Like, I want to find the fastest route to work. Well, I know how to calculate like the total time. The model is simple. The output is, well, how long it took. I want to optimize the output, meaning I want to find the minimum total amount of time it takes me to get to work. So the input is all possible routes I could take to work. I want to find the best one. So my goal is to find the best input to calculate and find the best output. Make sense? So the search space is the set of all possible inputs. Now we know, like if we're using the route to work example, the search space is huge. It includes all possible ways to get from my house to work. That's ridiculous. But of course, if I were realistically starting to look for the best, like if I want to optimize my route to work, am I really going to consider all possible routes? Well, no. I'm only going to consider reasonable routes, right? So we can constrain that search space a little bit. Like I'm not going to try to get to work by going through Toronto. It doesn't make any sense, right? So we can, simplify it a little bit. The search space. Okay, the search space would be all possible paths to work, though most paths would be terrible. So it's common to constrain the search space. For example, assuming living and working in the same town, don't consider going through another town. Has anyone heard of the traveling salesman problem? If you haven't, well, you're going to become very familiar with it. It's a relatively simple problem to understand, but it is of the classification a really goddamn hard problem. So the traveling salesman problem is a classic optimization problem. People will call it a toy problem. Now, one time I had a very obnoxious individual complain to it's not a toy problem, it's an important problem. Shut up. It's a toy problem because we're using it as an example, a toy to play around with and understand. No one's making a comment about the importance of this particular problem and finding good solutions and what it means. We're using it because it's an easy to understand problem. It's easy to understand configurations of solutions, but it's very difficult to find the best solution. So TSP is a classic problem. It can be modeled as an undirected weighted graph. So imagine I have a weighted graph, right? When I say graph, raise your hand if you know what I mean. Raise your hand if you don't know what I mean. So like 2/3 of the class didn't raise their hand. So wake up or leave. A weighted graph, what is it? Who raised your hand if you don't know what a weighted graph is? It's fine if you don't know what it is. I just want you to participate. Raise your hand if you don't know what a weighted graph is. Okay, perfect. All it is, you probably know what it is. I'm just using fancy words. A weighted graph is, we have a graph. Raise your hand if you've taken 255. Raise your hand if you're currently taking 255. Okay, so that you have an excuse, and you have an excuse. No one else has an excuse, because I know you've learned this in 255. If not, I need to talk to your professor. We have a graph. Right? There we go. That's a graph, a network. And if it's weighted, they have weights to it. 5, 1, 7, 2, 7, 1. I don't know. I pulled these out of my ass. Doesn't matter, right? So there's a weighted graph. So pretend that each of the vertices or nodes in this graph are a city or a location, a place you might want to visit. And the edges, the lines connecting the vertices, the nodes, these are how I could get from point A to point B, right? I can get to, from here I can get to here through this way. Maybe this is a road. Or I can go this way, or I could go this way, right? I have multiple ways. right? And what's the fastest way? Well, this way. Actually, for fun, let's make this a 2, right? That's a 2, not a Z. It's not a backwards Z. So, or an N. If I want to get from here to here, what's the fastest way? Where I want to minimize the sum of the weights. Maybe the weights are things like distance or time or number of potholes, I don't know. I want to minimize the total weights along my path. Well, naively, you might look at this and be like, oh, like that. Well, no, because that has a total weight of 5. But if I were to go this way, that has a total weight of 3. So maybe there's a lot of traffic on this road. And if I take these 2 side roads, I can get there faster, for example. That's the idea. So what I want to do is, usually with TSP, it doesn't have to be the case, but often you have a completely connected graph, meaning you have a graph where you can get from any point to any other point. Did I miss anything? Looks pretty good. Pretend everything's connected to everything and they all have a weight assigned to it. I am right here. I'm a salesperson. So a little briefcase. And I want to visit all these locations. Okay? And this is my home. I live here. And I want to visit all of these locations, start at home, end at home after visiting all locations, and I want to travel the minimal possible distance. That's the problem. So I'll just read it again. TSP can be modeled as an undirected weighted graph. Undirected, that just means there's no arrow. Sometimes you have a graph where you have like an arrow, which means you can only go that way. So often we don't consider the directed graphs. We have an undirected weighted graph, such that cities are the graph's vertices, paths are the graph's edge, and path distance is the edge's weight. It is a minimization problem starting and finishing at a specific vertex after having visited each other vertex exactly once. Is this clear? This is the traveling salesman problem. Effectively, the problem is to find the shortest Hamiltonian cycle. So here is a simple graph. It's a graph with 4 cities, and I want to find what path should I take to start at A, visit all other cities, and return back to A with the minimal distance. How do I do it? Any questions so far? All right, so to think of this in terms of 3 parts of a system. Given a Hamiltonian cycle, that's the input, because this is an optimization problem. The search space is all possible Hamiltonian cycles. For those of you that don't know, a Hamiltonian cycle is just a fancy way to say exactly what we were talking about. Start here. You ever play those games as a kid, like draw this picture without lifting your pencil? Those are Hamiltonian cycles. Technically, those are Hamiltonian paths. A cycle is a Hamiltonian path that starts and ends at the same location. Right? Basically, I want to hit all of these points once and only once. I don't want to ever lift my pencil. And I want to start and end in the same location. That's a Hamiltonian cycle. Okay? So given a Hamiltonian cycle, sum the edges of the weights in the cycle. That's the model, the calculation of the total distance. And the output is the total length. But this is an optimization problem. I have a lot of possible different Hamiltonian cycles. And I want to find the one that produces the smallest output. So this is an optimization problem. This is the description of a system, not the description of an optimization problem. I framed it as an optimization problem. Find the length of all, okay, so to frame this as an optimization problem, find the Hamiltonian cycle that produces the smallest possible cycle length. There are trivial algorithms to solve this. It's so easy to solve this problem. This is the easiest problem to solve. All I have to do, go with me on this, it's relatively simple. And I realize half of you in here have heard me say this before because I use this example a lot in different classes. How do I find the shortest possible path length? It's trivial. Take every possible Hamiltonian cycle, calculate its length, its total distance, and then pick the smallest one. Simple, right? How many cycles are there? Well, okay, I find every possible cycle, right? If we go back to here, I could go, let's say it's here, I could go A to B to C to D to A, or I could go A to B to D to C to A, or I could go A to C to D to B to A, or A to C to B to D to A. I got a bunch of different possible routes. All I have to do is find every possible route, every possible cycle, sum up the total distance, and then pick the cycle that has the smallest distance, right? So why is this a difficult problem? Well, so it turns out, so the starting ending city is always fixed. Given the 4-city example above and a set starting city, how many cities are there that could be visited? 3. After that, after we pick a city, right? How many possible cities are left to visit? 2. And then after that, there's only one possible one to remain. So, like, here's me showing every possible route. We can go A, B, C, D back to A, B, D, C back to A, C, B, D back to A, D, C, B, A, and so on and so on and so on. That's where we are. So far, so good? It turns out, like, so this is basic. I'm going to explain this to you, but remember, if this is not immediately clear to you, it's because you're overthinking it. Because I guarantee you, you'll learn this in like grade 6. It's about combinations of things. You probably got a problem in grade 6 that said, if I have 2 shirts and 3 pairs of shorts, how many outfits do I have? Well, you do 2 times 3, right? Because for the first shirt, you have 3 options. And then for the next shirt, you have 3 options, right? It's just, you just multiply it out. Now here I have, assume these are all connected. I have 1, 2, 3, 4, 5, 6 cities. How many possible orderings of these cities can I do? Well, the first one's fixed, right? Meaning I have 5 cities I could go to. So how many cities could I go to? 5, right? Now let's say I pick an arbitrary one that's a stand-in for one of the 5. Which one I pick doesn't really matter. But I have 5 options. So after I pick this one, how many options do I have left? So I have 5 times 4. How many do I have left? Then obviously 2, and then, well, 1, but that's useless, multiplying by 1. So how many possible combinations do I have of 6 cities? Well, really it's kind of like 5 cities because 1 is fixed. It's stuck. We can't change it. 5 times 4 times 3 times 2 times 1. Well, what is that? 5 times 4 is 20 times 3 is 60 times 2 is 120. There's actually 120 different possible routes of 6 cities. Well, 5, you know, if 1's fixed. All right? That's a lot. But okay, whatever. Now, we can play a game where we kind of prune this, where you consider, well, the ones that are the same forwards and backwards, we can kind of ignore those. And anyways, but at the end of the day, the total number of possible cycles of 6 cities where 1 is fixed is always going to be, it's always, oh no, of the 6, pardon me, of 4 cities, it's always n, where n is the number of cities, n minus 1 factorial, right? So 6 minus 1 factorial, well, that's 5 times 4 times 3 times 2 times 1. That's how many possible combinations there are. Cool? Happy? Sad? Angry? Joyed? Thumbs up. Good. So that's how many possible combinations there are. So when we had 4 cities, we had 3 times 2, 6. If we were to have 5 cities, well, that'd be 4 times 3 times 2. Well, that's 4 times 3, that's 12, times 2 is 24. And then with 6 cities, we're at like 20, we're at 100, wow, we're growing fast, right? We're growing really fast. So, you know, we could play a game where it's like, okay, half of the cycles are the same forward and back as backwards. What I mean is, A, B, C, D, A is the same as A, D, B, C, A. It doesn't, like, going one direction with the same backwards, it's the same cycle, it's just in reverse. It doesn't really matter, right? Basically, if I were to say, I want to walk to you and then to you and back, and I want to find the shortest path, what's the shortest path? Well, it doesn't matter if I go from here to there to there to here, or here to there to there to here, it's going to be the same. It doesn't matter, they're equal, right? Their sum is going to be equivalent because of cumulativity. Whatever the one of where the order of addition doesn't matter, it doesn't matter. Cool? So really, if we could get a little bit more precise, here I'm just saying the cardinality of the set V, where V is the vertices. That's just the number of cities. So the number of cities minus 1 factorial divided by 2. That's how many there are. Now, if I gave you an example of 100 cities, how many possible combinations are there? 4.666311 times 10 to the 155. That's a lot. That's a lot. To put things in perspective, there's about 2.4 times 10 to the 60 atoms in the Milky Way. You would need a shit ton of Milky Ways. If I were to take every possible combination, every possible path, I've got a giant list of paths. We agree, do we agree that, okay, yeah, that's a lot of paths, but if I go through each one, calculate its total distance, and then just do a linear search for the smallest number, I will find the best path. We agree to that, right? It's a trivial algorithm. The issue here is once we start to get to combinations of things. You know, it's kind of funny. Humans really suck at wrapping their heads around big numbers. And when we're talking about things like atoms in the Milky Way, I mean, at that point, like, how many atoms are there in the universe? How many atoms in the universe? About times 10 to the 78 or times 10 to the 82 atoms in the known universe. So like when we're talking about like physical things, we're running out. If I were to, we are orders of magnitude, like 100 orders of magnitude. We need like, what was it, 155 zeros. Right? Like, not only is it hard to wrap our head around a number like 10 times 10 to the 82, okay? That's a big goddamn number. And if you were to think of like, if I were to think of like physical things that exist in the universe, and I know it sounds like, oh, in the universe, like literally physical things that exist. I've got that many, like times 10 to the 83, well now there's no more physical things that I can even look at. Like we're out. And we're talking about times 10 to the 155. And that's for 100 cities. 100. That's not even a lot. 100 cities? That's not much. So, like if I were to take each possible path and assign it to an atom in the universe, I will run out of atoms really fast. Really fast. It'll be a drop in the bucket compared to the, like I will have so many left over. I would need times 10 to the 82, 150 for like 70. I would need like 70, 68, no, plus 5, 68, 73. Not 73 more universes, 73 times, like multiples. Like you'd stop trying to think about it, I guess, is what I'm trying to say. Like we can't. So like, oh wow, how many physical things are, like as soon as you start talking about combinations of things, we have what we call like combinatorial explosion. You ever hear that word before? A combinatorial explosion. As soon as you start to have combinations, the numbers grow so rapidly that it's just like unworkable. So once you start dealing with combinations of things, that's where you get really big numbers. That like we just, whatever, right? So that's where we have an easy solution to the problem. Okay, so let's say, for fun, 155 times 10 to the 155. So 1 times 10 to the power of 155, okay? Yep. Let's say we have a computer that can calculate the sum of the distance. Let's say trying to think of the best way to kind of like put this in perspective. If I could calculate, let's say, 1 trillion paths a second, okay? All right, let's say I can calculate 1 trillion paths a second. I've got the world's best supercomputer, and I can calculate the total distance of 1 trillion paths a second, right? So how many seconds would I need? Well, let's divide that by 1 trillion. 1, 0, 0, 0, that's billion, million, thousand, no, hold on. Okay. Trillion, billion, million, thousand, 1. Okay. You know what? Hell, let's make it quadrillion for fun. Quintillion. What comes after quintillion? Septillion? No. Hextillion? That's septillion. Octillion. I don't know what you call 9. Dectillion? There. That's we're at 10. Okay, that didn't make a ding. We can calculate a dectillion. I don't even know if that's what you call it.
I think it's decillion.
Decillion, there, that sounds a little nicer. Decillion, whatever you call it, that many a second. Are we anywhere near capable of computing that many things? No, of course not. That's ridiculous. But let's pretend we can. That's how many seconds we would need to solve this problem. Okay, well, how many seconds in a million? Okay, so let's do that. Let's calculate that. I'm just going to do that. No, I guess it's going to keep it. So let's divide that by 60 seconds in a minute, divided by 60 minutes in an hour, divided by 24 hours in a day, divided by 365 days in a year. This will tell us how many years. Okay. So how long has the universe been around for? Like 13 billion, something like that? Okay, so let's just divide that number by 13 billion. 1, 3, 0, million, thousand, 1. Okay, we would need that many universe. Okay, it ain't happening. Okay, although there is a simple algorithm, because of the number of combinations. Point is, these are big goddamn numbers. And that simple algorithm, yeah, it's guaranteed to work. But we need orders of magnitude, like so many orders of magnitude, more time than the universe has existed to be able to do it by calculating this many a second, which is not even possible. So that algorithm ain't going to work, right? Pardon? The heat death might come before that happens, unfortunately. So entropy might, kind of wipe out. So not only, I don't know, what's the estimation for when heat death will happen?
Google it.
Yeah, let's find out. When will When will the heat death of the universe happen? 2023. That's so. Oh yeah. So yeah.
7 to the
Yeah. So even if. Oh, we might do it. We could do it. We'll just be able to do it. For those of you that don't know, heat death is when like basically the universe hits equilibrium and nothing interesting will happen. It's done. So it looks like we're in luck. If we could calculate, starting now, maybe next year we'll unlock something good with computers and we can figure out these solutions pretty quickly. Maybe quantum computing will magically solve this problem like that. I don't know. And if it does, okay, great. Crisis averted, I guess. But these are big numbers. Point being, a simple algorithm like that, although it exists, it's not going to work. So if I told you find the best path for 100 cities, you can't start finding all possible combinations. It ain't going to work. We need to come up with another solution, another way to find a solution. This is where like the AI and optimization comes in, where we go like, okay, look, we ain't going to find the best solution because the search space is just catastrophically large. It's not going to happen. But maybe we can find a sufficiently good solution in less than 155 times 10 to the 155, durations of units of time, right? It's much better. It's not necessarily optimal. It probably won't be optimal, but it'll be good enough. Because I didn't have to wait for multiple orders of magnitude, like a lot of orders of magnitude longer than the universe has existed. Because I can find it now and not, And you're going to do that for assignment 1, which is posted, by the way. I think the deadline is actually live now, if you can verify that. So here's another one, n queens. You ever hear of this problem before? It's another one of those problems. It's a toy problem. Again, that's not to say it's not interesting. It's to say that we like these problems because it's easy to wrap our head around the problem and what it means, but it's sufficiently difficult that we just can't find a solution. It's difficult to find a solution, but we can understand the problem and strategies well. So n queens, given some n by n, so often this, like the simplest case will be like 8 queen. Not simplest, but like a common case is 8 queens because a chessboard is 8 by 8, right? Right? Yeah. An 8 by 8 chessboard with 8 queens or an n by n chessboard with n queens. The goal is I want to be able to place the n queens on this board such that they're all safe. None can like directly attack another one, right? So here's a little GIF of doing like a depth first search to find a configuration that works, right? So see, like, okay, it's trying until, oh, no, they attack, and then so it keeps going and then backtracking until it finds a workable solution. So unlike TSP, this problem is a little different for optimization because there's nothing to be minimized. See, what's nice about TSP is each solution, it's possible to have two solutions that have the same total length. But there's like a reasonable gradient. Like if there's a lot of cities, each with their own weight, if you were to take all possible configurations and add them, there's going to be a lot of different possible like sum total lengths, right? And there's like a gradient, like one that took X, like 100 units of total distance and one that took 99, well the 99 is better, it was less distance. This one's a little different because it's more of a, what do they call this? It's not, there's a name for something like this and I can't think of it right now, but basically it's not like, it's basically correct or not. Is it a valid configuration or not? TSP, all possible configurations are valid, it's just what's one's the minimal. This one's different. It's, is this configuration valid or not? Do you see what I mean? It's yes or no, where TSP is, can I find a better distance? Can I find a better distance? This was, here's a configuration. If you say, is there a better configuration? I'd say, It's a configuration. There's no better. It's valid. Clear? So n queens. This is the 8 queens. It's binary. It's valid or not. So how many board configurations are there? Well, how many configurations of 8 queens are there on an 8 by 8 board? Well, this is if you remember your basic statistics. And if you don't remember, that's fine. But it's 84 choose 8, which is 4,426,165,368. That's how many. That's how many possible configurations there are. However, there's actually 92 valid board configurations. So of all of those possible configurations, only 92 are valid, which is interesting. So on an 8 by 8 chessboard, there are 92 possible configurations of n queens where they're never like attacking each other. Is the problem clear? When I say attack, raise your hand if you're reasonably familiar with chess. Okay. No, you're not? Okay. Really? Oh man, that's cool. It's rare to find people. Okay, that's neat. So basically, do you know how queens move? Yeah. This is actually important, okay? When I ask familiar with chess, I don't mean you don't have to be good at it. You just have to know the rules. So the idea here is a queen. Do I have a picture of a queen? Do I just have? So usually each player only has one queen, okay? And this is like a queen. And a queen can move diagonally, however far it wants, and like vertically and horizontally, however far you want, okay? Now, this is a valid solution because there does not exist a queen here that can directly attack another queen, meaning none are in the same diagonal and none are in the same row or column. That's what it means, right? So see, nothing here, nothing here, nothing here, nothing here, nothing here. So I mean, you might even notice, it's kind of interesting. There must be, like, look, if I have an n by n chessboard, and I need to place n queens on this, okay? There's n rows and n columns and n queens. And they can attack the same rows and columns. Can you ever find a possible valid configuration where 2 queens are in the same row or column? No, because they would therefore be attacking. Meaning, you can flip that to conclude, logically, that for any valid configuration, there must be one and only one queen in each row, or column. Right? There must be, which is kind of neat, but more on that a little later. So there you go. N queens is find a configuration such that none are possibly attacking each other. Cool. So how many board configurations are there? A lot. NASA's problem. So see this fancy little, like, I don't know, what do you call that? Truss structure. Cool. Right? Versions of a structure like this were designed by genetic algorithms that were way stronger than anything that any engineer would design. And I mean, it's kind of neat too. I mean, here's another one. See this? This is a little antenna. It's actually tiny. There's another picture of this antenna next to a quarter. Like the quarter's like right here. It's tiny. That's centimeters. That's tiny. Itty bitty. Look, it's such a small picture. Look how like pixelated it is because I had to zoom it in. A tiny little antenna. That antenna is in space. No engineer designed it. A computer did. This was designed, and this is so goddamn effective at picking up the signal it's designed to pick up. But no human would look at this, because if you picture an antenna in your head, do you think of something like that? This does not conform to a typical idea of what an antenna looks like. I wish I had the picture of what these ones look like. I have a picture somewhere. NASA Truss GA. Yeah, there you go. Something like this. This might not be the one, but it looked like something like. Yeah, the GA, there you go. I don't know if this is the one, but like they were designing trusses that look like this. No engineer in there, that does not conform to typical designs that any human's familiar with. And what's kind of neat about like the computers is they're not constrained by what we expect. You and me, we have preconceived notions of, I want to build a truss. I know what trusses look like. That doesn't mean the way we expect it to look would be a good one. So it's kind of like a little bit more open-ended. And that's actually a neat thing when it comes to like computer design, is you want to, sometimes we might think we're constraining it based on what we know is good, but we are introducing our own biases, which is interesting. Okay, and then there's modeling. So we just talked about optimization. Modeling, on the other hand, is given a system, if the goal is to find a function and process to produce the output, then it's called modeling. So writing software is modeling. Sometimes it's simple, like writing a program to calculate the grocery bill, but sometimes it's complex, like writing a classifier for letting you know, based on petal widths and heights and sepal lengths and widths, what type of flower it is, right? So that would be modeling. I want to write a function that, given a length and width and a length and width, tell me what type of flower this is. Okay? That's a little bit more hairy than writing a function to calculate the grocery bill. So modeling. I want a good classifier, for example. When using machine learning and AI optimization for modeling, one can think of modeling as an optimization problem. You can, where you think of all possible configurations of a model, and then you want to optimize the one that gives you the best output, the best accuracy. So you can think of modeling as optimization if you just kind of flip it around a little bit in your head. So find the best classifier setup. Find a classifier model to classify the iris's inputs such that the error output is minimized. So sometimes we can frame modeling problems as optimization problems if you think of the process of finding a model as the search space, which is kind of interesting. We're going to be doing this when we start talking about genetic programming. And then real-world problems. Yeah, whatever. And then simulation. This one's a little easier. Given some input, given a model, run it, what's the output? We do simulation all the time because sometimes if you want to know what's going to happen, if a volcano erupts on an island full of people, well, we're not going to do that experiment in real life. We want to simulate it because, you know, ethics are a thing. So that's like simulation. A lot of times we're not so focused on that in the AI machine learning optimization stuff. And we'll pick up here next time. Cool. Any last questions? Cool. All right, I'll see y'all later.